Okay, now let's talk about logarithmic equations. And our goal in this case is that we're given a logarithm, but this time we want to isolate x, and x is contained in the logarithm. So what do we do? Well, one thing that we could remember right away is that by definition, if I tell you that the logarithm base a of x is equal to y, then I know that x is equal to a to the y. So I can actually use my properties of logarithms in order to get x isolated. I put it together, right? So here's what I'm going to do. If I say log base 3 of x is equal to 5, what's the interpretation? In this case, that says, well, 3, when raised to some power 5, gives me x. So, well, in this case, a good way of thinking about it is that, well, that would mean that x would have to equal to 3 to the 5th power. Now, if it helps you, a good way of visualizing this is that just like we could take a logarithm on both sides of an equation that contained exponents, we can exponentiate on both sides. We could say, well, if we imagine it like this, 3 to the logarithm base 3 of x is equal to 3 to the 5th. In other words, treat both sides of the equation as an exponent. Well, note that we have 3, and it's raised to the power log base 3. What happens in that case is that those two things cancel each other out, and it just leaves us with x. And so x would equal to 3 to the 5th, and if you work that out on your computer, you know that calculator, you know that 3 to the 5th is the number 243. So that's not bad. Here's a little bit of a harder example. Let's say that we have the logarithm of x plus the logarithm of 2x equals 5. Now we don't see a base written, therefore that base is considered to be 10, right? Because it's a common logarithm, right? Base 10. So we keep that in mind here whenever we're looking for this guy. So let's see, what do we do? Well, in this case, it's not as though we can just raise both sides to 10 because of this addition right here, right? We got a little bit of trouble with that, so we have to figure out what to do. And this is where we're going to use our rule that says if we have a logarithm of a quantity a times b, it is the same as the logarithm of a plus the logarithm of b. That's our sum rule. Now, if you remember that, in this case, what we're going to have to do is that we're going to have to combine these two quantities on the left, and we're going to get the logarithm of x times 2x. That's 2x squared is equal to 5. Well, that's interesting. Okay, so now we've got a logarithm of 2 times x squared, right? That's what we're taking the logarithm of, is equal to 5. It's a base 10 logarithm. So just like we exponentiated on the left, we could exponentiate on the right. And we might see this, that, well, okay, if this is a base 10, then 10 to the log base 10 of 2x is just going to be 2x squared. And that's going to be equal to 10 to the 5th. Ooh, okay, things are getting a little weird here, but all right. Well, 10 to the 5th, what is that? That's a 1 followed by 5 zeros. All right, so if we wanted to treat it this way, that's a 1, 2, 3, 4, 5, 100,000. And so we've got 2x squared is equal to 100,000. We'd want to get x squared by itself next. So we're going to say, well, x squared is going to be 100,000 divided by 2. That's 50,000. And if I have a square, of course, that means I'm going to want to take my positive or negative square root. But in this case, in fact, the only number that's going to work is whatever the square root of 50,000 is, right? And, well, I mean, we can certainly reduce the radical. We can do all kinds of things right here. But look, there's an answer. Now, we're not going to say use the negative, right? We can't use the negative square root of 50,000. Why? Well, very good, right? Go back over here to the logarithm. We cannot take a logarithm of a negative number, right? So logarithms of negatives don't exist. So our only solution will be whatever we would get for the square root of 50,000. You probably don't even need to get your calculator value for that one, although I'll give you some more points if you reduce. All right, so there we go. That's an example here. Let's do one more. Let's try one more. All right. And this time we're going to use this property right here. This is another kind of logarithm property that we run into. It basically goes like this. If we have an equation where log base b of x is equal to log base b of y, then it must be that x is equal to y, right? And if you remember when we started out with the exponential equations, it's the same sort of idea that happened with exponents. So that means that what we're going to have to do is we're going to have to simplify this expression a little bit. Now on the left-hand side, I've got 2 times the logarithm base 2 of 3 minus log base 2 of x. I don't want this 2 in front. So what I can do is use my power rule, remember, and that's going to tell me that this is the same thing as the log base 2 of 3 squared minus the log base 2 of x. And that's equal to log base 2 of 45. Alright, log base 2 of 3 squared, well that's 9, right? And of course in subtraction, that means that we divide the arguments in each logarithm. So what's going to happen is that we're going to get the logarithm base 2 of 3 squared, that's 9, divided by x, and that will equal the logarithm base 2 of 45. So we can use our properties to rewrite this. Right? We rewrote it once, we wrote it twice using our properties, and now we've got this situation where the logarithm base b of x equals the logarithm base b of y, only in this case, instead of x and y, it's 9 over x, and it's 45 on the other side. Well, a little bit of algebra here would show that what we're going to do is if we multiply both sides by x, we're going to get 9 is equal to 45 times x. And so to get x alone, we have to divide both sides by 45. And we might recognize that 9 over 45 is a fraction that reduces. This reduces to 1/5. 1/5. So x is equal to 1/5 is our answer. Now you could write this as 0.2, right? That's the decimal equivalent of that. But here it is. That is the example of having a logarithm that is the same on both sides. So several different kind of log equations right here. Pretty cool.